So the last speaker of this morning will be Frederico Girão from Federal University of Ceará, and he's going to talk on geometric inequalities for hypersurfaces in space forms.
Thank you, Walcy. I want to thank Davi and Jorge as well for the invitation. Okay, so let me start with inequality by Kwong. Okay, so sigma is a hypersurface embedded in Rn, and we call omega the region enclosed by sigma. Okay? So I'm going to say that sigma is strictly mean convex if the mean curvature of sigma is strictly positive. Okay? Então, what Kwong showed is that if you integrate the distance from sigma to the origin, this is greater than or equal to n times the volume of omega. Okay? All right, and also if the equality holds, then sigma is a sphere centered at the origin. So we know that there's a parametric inequality that says the following, that this power of the area of sigma is greater than or equal to the volume enclosed by sigma. So you can ask the question, can I improve Kwong's inequality to this inequality here? In other words, can I change the volume of omega by the power of the area? All right. So okay, if this is true, if you can use Holder's inequality and get this inequality here. Okay. Well, we see later on that this previous inequality is not true. Okay. There's a counterexample, at least in dimension n equals 3. All right. All right. But what we can do is like an average of Kwong's result and this inequality that I just said is not true. Okay, so this is a result with a student of mine. If sigma is star-shaped and strictly mean convex, then the integral of R is greater than or equal to the power of the area plus the volume of omega. And the equality holds if and only if is a sphere centered at the origin. Okay. So I'm going to call this inequality by improved Kwong's inequality. Okay. In this case of the Euclidean space is an improvement. In hyperbolic space, it's not clear if it's an improvement or not. Okay. As a consequence, you can throw away the volume term here and get this inequality. All right? And then by applying Holder's, you get this one. All right, so the idea is to use the inverse mean curvature flow, okay? So here's the flow. You flow by the inverse of the mean curvature, all right? And there are some results that if you start with, that said that if you start with strictly mean convex hypersurface in a space form, then the flow exists for, in the case of the hyperbolic space and the Euclidean space, the flow exists for all time. Okay? In the Euclidean space, you also have that the rescaled hypersurface converges to a sphere. Okay? It's by Gerhardt and also by Urbas. All right, so the variation formulas for this flow are very nice. So the volume element, the derivative of the volume element is the volume element. The derivative of the area is the area. And if you compute the variation of the volume of that the sigma encloses, this is the integral of 1 over h. All right? Okay, so the idea is to consider this quantity here, all right? And use the inverse mean curvature flow and show that the quantity is non-increasing along the flow, and then try to see what happens when t goes to infinity, okay? All right. So if you prove this, then you get the inequality, because you're going to get the Q of 0 is non-negative. Okay? Okay, so here's the computation. All right, it's a simple computation, but the thing is that when you compute the variation of this is less than or equal to the variation of the volume of omega plus the integral of r. Okay. All right, so it's very nice because this term here is going to cancel with this one when you compute the variation of that quantity Q I defined. Okay. And then right here, you actually need the Kwong's inequality, the original one, okay, to conclude. Right? Okay. And then you use that the flow converges to a sphere to analyze what happens at infinity. Okay. and then you show that at infinity is greater than or equal to 0. So you have your inequality. Okay. Okay, so what happens when we change Euclidean space by hyperbolic space? In this case, the inverse mean curvature flow is more complicated. Okay. For example, it was showed by, I'm sorry, I'm going to get there. So Kwong has a version of his inequality in this setting. Okay, so I'm going to write the hyperbolic metric like this. Okay. Okay, so Kwong's inequality is like this. Okay, so integral of the hyperbolic sine greater than or equal to n times the integral of hyperbolic cosine over the region omega. All right. So we proved the version of our inequality in this case as well. Okay. And the idea again is to use the inverse mean curvature flow, but as I said, in this case is a little bit more complicated. Okay. For example, when n equals 3, it was showed by Wang and Hung that if you rescale the metric like this, it may not converge to a metric of constant curvature on S2. Okay, so it's a little bit strange. So once again, you define some quantity, and you compute the variation, and then you try to analyze what happens at infinity. Okay. Okay. So here's my quantity, and proving the inequality is the same as proving that Q of 0 is greater than or equal to 0. Okay. So a very similar computation to the Euclidean one. You get this part here, and then to get this is a little bit more complicated. Okay. So to get the limit, so I'm going to call the hyperbolic cosine by rho and hyperbolic sine by psi. Okay. To get the limit, we use that the Laplacian of rho is n times rho. Okay. And also use this inequality here. Okay. And then to show that the limit is non-negative, we actually show that this quantity here, this limit here, is non-negative. Okay. And to do this, you have to do some asymptotic analysis. Okay. So this is done in detail on a paper by Brando, Wang, and Hung. All right. So here, for example, the volume element, you can write it like this, okay, where alpha is something of this order here, right? And also, we use Holder's inequality, okay? All right, so let's take the sphere now as the ambient space. We write the sphere in polar coordinates as we did with the hyperbolic space, okay? And Kwong has a version of his inequality in this case as well, okay? So the inverse mean curvature flow was studied by Makowski and Shoya, okay? Also, Gerhard has a paper on the about the inverse mean curvature flow on the sphere, okay? And what they prove is that in finite time, well, if the initial hypersurface is strictly mean convex, strictly convex, then in finite time the flow is going to converge to an equator, okay? Okay, so this equator determines two hemispheres, one of them containing my hypersurface. Okay. Okay, so I'm gonna associate to my hypersurface sigma a point x, which I call I'm gonna call this point the point associated to sigma via the inverse mean curvature flow. So I flow my hypersurface, and this is gonna flow to a hemisphere, okay? And then, to an equator, and then I take the point x of sigma to be the center of the hemisphere determined by this equator. So if this point is the origin, then I'm gonna say that sigma is balanced. So we also have a version of our inequality in this setting, but now we have to ask that the hypersurface is strictly convex, okay? And that it is balanced. Okay? So the proof is very similar. You consider this quantity, and you prove that the quantity is non-increasing, and that the limit as t goes to this t star, the time when the hypersurface becomes the equator, the limit is 0. Okay. All right, so let me talk a little bit about the Alexandrov-Fenchel inequalities. So in Rn, these inequalities, they say that the integral of the sigma k curvature, okay, this is the kth elementary symmetric function of the principal curvature vector, okay, is bigger than or equal to some constant times this power of the integral of the kth minus 1 curvature, okay. So in 2009, Won and Lee, they used some geometric flow to prove these inequalities, okay? And for their proof, they only needed the star shape, the sigma to be star-shaped, and k convex. K convex means sigma I greater than or equal to 0 for I from 1 to k. Okay, so it follows from these inequalities that the integral of sigma k is greater than or equal to this power of the area, okay? With the equality occurring if and only if sigma is around the sphere, all right? So these inequalities, they were used by Gi, Wang, and Wu in the proof of the Penrose inequality for asymptotically flat Euclidean graphs in the context of the Lovelock gravity, okay? All right, so I'm interested now in in weighted, what I call weighted Alexandrov-Fenchel inequalities. Okay, so in the Euclidean space, you can consider R2, R squared to be your weight, for example. Okay, so there's this result by Kwong and Miao. So they proved that for k from 2 to n minus 1, that the integral of R2 sigma k is greater than or equal to the integral of sigma k minus 2. Okay? And the equality holds if and only if sigma is a sphere centered at the origin. Okay? So as a corollary, we get that the integral of R squared sigma k is greater than or equal to this power of the area. All right? So the question is, does this inequality hold for k equals 0 and 1? Right? So when k equals 1, Kwong and Miao, they proved that the integral of R2 h, here's the mean curvature, okay, is greater than or equal to n times the volume of the region that sigma encloses. Okay? With equality occurring if and only if sigma is a sphere centered at the origin, a round sphere. Okay, okay, so so another result of mine with my student. So we actually proved that the inequality holds. Okay, if you change this for the area, for this power of the area. Okay, and the proof once again uses the inverse mean curvature flow. Okay. And we actually have to use Kwong and Miao inequality in our proof. Okay. Okay, so the k equals 0 case. Oh, so in this case, the quantity is just the integral of the distance squared. Okay. So this is known as the polar moment of inertia of sigma with respect to the origin. Okay? So there is this result by Beta, Brock, Mercado, and Posteraro that among the surfaces which enclose the same volume, okay, the sphere centered at the origin is the one with the smallest polar moment of inertia. Okay? Okay, so when n equals 2, Sachs showed that the minimum volume of this quantity here, so the power of this power here is such that when you rescale, it doesn't change, okay? So this quantity here, among all continuous convex curves, is attained by, so the minimum volume is attained by an equilateral triangle. So not a circle, okay? So this is a little strange. All right. And later on, Hall proved using Fourier series, okay, this result. So when n equals 3, there is this paper by Freitas, Logensen, and Liddell, and that they showed that a minimizer exists, okay. All right. So among the set of surfaces which are bounded of a convex body, okay? And also they show that the center of the sphere centered at the origin is not a minimizer. So for example, they computed for a tetrahedron and the quantity is smaller, okay? Okay, so question, so if you allow only smooth surfaces with positive mean curvature, is the sphere a minimizer? And the answer is no. So we found a counterexample by taking this curve here and rotating around the y-axis, okay? So this is inspired by the work of Fillmore, okay? So here's a picture. Okay, well, well, I mean, the result, work only with the area seems a little difficult, but we have this inequality here, okay, mixing area with the volume of omega, okay. All right, so as a consequence, you can throw this thing out, and you get the integral of r squared is greater than this quantity here. All right. Okay, so now I'm going to talk about weighted Alexandrov inequalities in hyperbolic space. All right. So I'm going to write the hyperbolic metric like this, and my weight is going to be the function rho, this hyperbolic cosine of r. All right. So there's this result by Guy, Wang, and Wu. If sigma is horizontalically convex and k is odd, then the integral of rho sigma k is greater than or equal to this quantity here that depends only on the area of sigma. Okay? And the equality holds if and only if is a geodesic sphere centered at the origin. Okay? So their proof is done by induction from k to k plus 2. Okay? So they only have to analyze the base cases, the case k equals 1 and k equals 0. Okay? Well, the case k equals 1 was like joint work with Levi-Lima. Okay? So from this case, you get all the odd ones. All right? And they're like, that's their result, only for odd k. Okay? But their induction work for even k as well. So they only have to show the base case, the k equals 0 case. Okay? Okay, so the k equals 0 case is this one. So there's this conjecture on their paper. So integral of rho is greater than or equal to this quantity here. Okay? Okay, so now I'm going to talk about this flow that I call support function flow. Okay, so you take, so D is the ambient Levi-Civita connection, and this is the metric, the ambient metric. So you take P to be this quantity here, and you consider this flow here. Okay. So it's minus you take minus p here as your velocity. Okay. So up to tangential motion, this is the same as moving sigma along the integral curves of this vector field. Okay. If you use the ball model, it's very easy to see that when you look at sigma from an Euclidean point of view, you're just like shrinking it like homothetically. Okay. Okay, so the variation formulas. So the variation of rho is minus p squared. We call p is this quantity here. Okay. This is the outward unit normal to sigma. So the variation of rho is minus p squared. The variation of the volume element is like this, okay? And the variation of the integral of rho is this. Okay? So if you use this formula here, this well-known formula, okay, you can compute, I'm sorry. You can compute this thing here, okay? Here, okay? Okay, so this is the formula I want, okay? So the variation of the integral of rho has a very nice expression, okay? And also, using this again, you can compute the variation of the area of sigma, and it is this one. Okay, so let me consider this quantity here. Okay, so I'm going to use this flow. Okay, and using these two variation formulas, you can show that this quantity is non-increasing. Okay. All right. So now I have to compute the limit as t goes to infinity. All right. And to compute the limit, we can use L'Hopital rule. All right. So this limit here is the same as this one. Okay. So once again, I'm writing the hyperbolic metric like this. So I can consider also the Euclidean metric on this manifold. Okay. So the idea here is that when I shrink the hypersurface, it's going to become very, very small, and at some point, it's not going to notice the curvature of the ambient. Okay. So after some analysis, you compute that this limit is the same as this Euclidean limit here. Okay. So to show the conjecture that Guy, Wang, and Wu they made, you only have to show this. Okay. But it turns out that this is not true. All right. This, like the same counterexample works. Well, the original conjecture is not true, but if you put this factor here, then you have an inequality. Okay. So these are two students of mine. Okay. So the integral of rho is greater than or equal to this quantity that depends only on the area of sigma, and the conjecture by Guy, Wang, and Wu, at least when n equals 3, is false. Okay. So let me show you the conjecture again. This one. Okay. Well, that's what I prepared. I think. Thank you so much. Okay.